All right, here we are, the multiple choice with my main man's Mexican. Put a thumb in. Yeah, buddy. Dion, get it in there. Oh, George. And Corby Corb. Safe, boss. Safe. All right. Maybe we'll cut that out later on. All right, let's go for the multi-choice. So for the first part of this, already you're very lucky if you've put C and you got a wrong answer. You can see the mark scheme was wrong. Upon checking, this graph goes up and X shows some plastic deformation at the top. So there's a curve there at the top, which basically is an indicator that it's not brittle. It's got some ductile behaviour. Y, on the other hand, it goes up and then shows no plastic behaviour, so it snaps or fails us at the end of that point of proportionality. So we'd say Y is the most brittle. So all these statements are correct, but C is the one that's wrong. So check that, people. You may well be worth an extra mark. Alrighty. Second question. The golf ball gives us a mass, that's all good. It gives us a speed of 95 meters per second, and it gives us the force on the ball. Now, if it's giving us mass and speed or a change of speed, okay, then it's a Newton's second law. So remember Newton's second law, we can say F equals delta mv over t, or F times t equals m delta mv. But whatever we do, it wants to know the time, so we're going to rearrange that to make t the subject, as you can see here. Yeah. Once you do that, the key to understand this, the key word really in this question is the word stationary. That tells you it starts off still and it ends up with a velocity of 95. So we can put in the mass, 4.8 times 10 to the 2, and the velocity, or the change of velocity, 95 minus 0. And that's the idea of going from stationary to 95. Once we divide that by the force applied, it pops out, and the answer comes to 5.8 times 10 to the minus 4. Any questions?
Could you not use like the impact for the impact formula?
Impact formula?
Yeah, it's like UT something plus VT all over the. I know. I did that and then I got the right answer. Okie
dokie. Yeah, basically, I think what you're probably doing there is you're basically just using the change of velocity.
Yeah.
Yeah. So really, it's to say, yeah, it will be a version of this anyway. It's the same thing. All right, that's good, man. This question, I love this question. Lots of things to take on board, lots of things to think about. And we need to understand it, you've got to, first of all, it asks us, we've got a string, we've got a 1 kg mass and a string, a 2 kg mass, and the string gets burnt. What acceleration does all things do when they drop? What's the rate of acceleration of anything when it falls?
9.81.
9.81, gravity. So we're looking here, this table here, the acceleration of the 2 kilogram mass downwards in meters per second. Is it going to be 1g or 2g? G being 9.81. It's going to be 1g, isn't it? It's going to be g. So straight away you can just scribble out that one, because we know it can't be that. And this is the process, this is the technique for answering these multi-choice questions. Yeah, so we know it can't be b, because that's just, it's got to be, the 2 kg mass has got to be accelerating at the rate of gravity, which is g, 1g. Now, let's think about the 1 kilogram mass. In order to understand what's going on with the 1 kilogram mass, we've got to think about the before and after situation. Before the string breaks, our mass here has got basically the weight of 3 kilograms acting down on it, hasn't it? So that's 1 kilogram plus 2, that's 3 kilograms, times by 9.81, so it's 3g, because W is m times g, the weight. 3g is the force acting downwards. Does that make sense? So that'd be 3g in newtons. Because it's in equilibrium, the tension acting up from the string must also be 3g, because it's not accelerating up or down. Make sense? Yeah? So when we so that tension of the string there is 3 times g. As soon as the string breaks, or the string is burnt off, there must, for that first instant, there must still be a force of 3g acting up. Yeah? Now, the 2 kilogram mass has just fallen down, so we have 1g, the weight of the mass, still acting downwards, correct? So we've got 3g of force acting up, 1g of force acting down, and therefore the net force will be 2g acting upwards. Now this is 2 times 9.81 in newtons, yeah? This is a force, not an acceleration, yeah? But that is a force upwards of 2 times 9.81. Once we then look at that, well, we can say, well, we can now say that force, if we put that into F equals ma, we've got 2g acting up. The mass that we're accelerating, of course, is just 1 kilogram. So that's 2 to 2. So basically, we'd say if you use F equals ma, it would be 2g is the force, equals 1 is the mass, times by the acceleration. Of course, you can see from that the acceleration will be 2g. Does that make sense, lads? Yep. So that gives us C. Okay, so these questions here, now these questions, in this case, this one's fairly intuitive and fairly obvious, but it's a technique to doing all of these which we need to get our heads around. Now, I'm going to get rid of all this. We basically know that when it falls, the mass times the gravity times the height is equal to mv squared, okay? So we've got mass on both sides and get rid of that. We can take the gravity over to one side, and what we basically find is that the height, yeah, is proportional to v squared. Does that make sense? Well, d is proportional. In this case, it's saying it's falling apart. D, it's got a velocity v. So we can say that d is proportional to v squared. Sorry, proportional to v squared, and therefore d is proportional to the square root of v. Does that make sense? That statement there. Oh, sorry. So no, I got that wrong. V is proportional to the square root of d, that statement there. Sorry, I'm talking pants there. There you go. So V is proportional to the square root of d. Now, once you've got a set statement like this, a proportionality statement, to solve questions like this, if you're changing one factor, we want to see what's the effect of changing d. What you do is you say, well, V prime, the new V, okay, will be equal to the new d times by the old v. Okay, and it's basically a consequence of what you really do. You say if v primed equals is proportional to d primed, square root of d primed, and v is proportional to the square root of d, then what you do is you're basically dividing one equation by the other equation and then taking the v across. And so this gives us v prime equals d prime times by v, and of course, basically, the first d would be the original d1. This is now 2, so it's going to be the square root of 2. Yeah? These are really sort of tricky, and what I think I'll do is I'll put together a whole sample of this style of question and give us a big practice on these, or the things that don't even apply, which aren't even on the syllabus necessarily. But you can think of it with logic as well. If d is proportional to v squared, if we double d, if we doubled v, that should be 4 times as big, shouldn't it? So you can actually go through these and say, well, none of these will work just because they're illogical anyway. But that basically gives us v primed is equal to the root 2 times by v. So it's d. Tricky question, that one. For this one, me and Christy both ended up playing ping pong. We'll take tax to them because I spotted the mark scheme was wrong on this one as well when I was first marking it, and Christy was still at work. Here we have to look at this question. Velocity here is velocity versus time. Now remember, the gradient of a velocity time graph is the acceleration, isn't it? Yeah. So here and here we got no acceleration. At the top, at the start and the bottom, we got no acceleration. Now, if we think the gradient is equal to the acceleration, and acceleration is equal to the force over mass, that's Newton's second law revisited, yeah, then acceleration must be proportional to the force, yeah? So here, if there's no acceleration here, can there be any resultant force? No. And if there's no acceleration here, can there be any resultant force? No. So armed with that alone, all you can do from that is you would go, well, which of these two's got no force at the start and no force at the end? It can only be A. Yeah? If you want to think it a little bit further, where is the acceleration the greatest? It's right in the midpoint, and the rest of it's getting to be less. Does that make sense? So here we've got increasing gradient, increasing force, maximum gradient, maximum force, constantly decreasing gradient. Okay? And therefore, we have this situation. Now, looking at this, because it's got a little flat bit in the middle, I would have said the graph should look something a bit more like that. Do you know what I mean? But it doesn't matter. Alrighty. So that gives an answer of A. Now, question 6. We know that work done is force times by displacement direction of the force, yeah? Work is F delta S, yes? Now, when we are, that has led to, this statement here has led to all those equations that we use for area, for the work done in stretching a spring, assuming the spring's a straight line, it's a triangle, isn't it? So that's that half base times height equation and stuff like that. But the bottom line is that the total work done is the total force times the total displacement. So it ends up being the area under a force time graph. Yeah? Now, therefore, the area in a force times graph is work. Work is joules, work is energy, yes? Therefore, we need to look down this and say, which of these is energy? Yep. It's as simple as that. And there's only one of them that is energy, and that's B. All right, that's the multiple choice section. We'll stop there.